I shut the light off in the office here so nobody could look in and make faces at me or anything.
Well, we are live. So just like to welcome everybody to the Amatec Solid State Controls webinar this morning. Obviously, if you're in the United States, good afternoon and good evening to anybody else that's out there in different time zones. And thank you for joining us today. Once again, we always like to say we appreciate your time. We know it's precious. So the fact that you're taking some time out of your day to watch this webinar is really appreciated. My name's Craig Williams. I am the Senior Technical Manager for Amatec Solid State Controls. And it's usually me who does most of the webinars. But today, as in a couple of weeks ago, we have Don Imlay, our training manager, who will be taking the webinar today. He's going to be going over everything. And at the end, if you have any questions, Don will answer most of them. But if I see any that I can answer, I will do that too. So we use Webinar as our Webinar Jam as our provider. So there's a few things that I'd like to go over. First of all, if you hear my voice and then type in a question in the question bar, it takes about 30 seconds for us to see that question. So because Webinar Jam has to send all of its streaming services out to an iOS device, to Windows devices, to Android devices. So there's a little bit of time taken to do that. It takes about 30 seconds. Also, what I always like to start off with is, if you can hear me, please type in the chat bar and let me know that I'm not talking to no one and that you can hear me. That's always a good start as well. And also, Webinar Jam has a panic button. We've never had to use it. It's a very stable service. But what that does is, if for some reason the service does get stuck or something goes wrong, we can press the panic button. And I think what happens is everybody gets sent to a new room. Everything starts again, and we can carry on going. Thanks, everybody, for letting me know that you can hear me. So that's absolutely perfect. Good stuff. As usual, what we usually ask people to do is, you can ask questions using the chat bar at any time. We do try to wait until the end of the webinar to answer any of the questions. But if there is something pertinent and we do see it and it is relevant to what we're discussing, we may try and answer it as we go. But it's better that we leave all of the questions to the end. But that doesn't mean you can't type a question in whenever it comes up in your head, and we will try and answer them at the end. So without further ado, I'm going to move on to the next slide, and I will introduce you and hand it over to our training manager. His name is Don Imlay, and he can introduce himself.
Good morning. This is Don Imlay. As you see here, I'm the training manager at Solid State Controls. I've been doing this full-time for somewhere around 20 years, and I've done, I'm guessing, about 300 of these seminars, or 4-day seminars that we do. That's not to say I know everything, but I have had some experience with this somewhat. Of course, this is a kind of a new thing for me, only my second webinar, but I'm going to try to treat it like I would in a regular training class. I've been here at SCI a little more than 35 years. All that means is I've learned a few things, but again, I don't know everything. And if somebody asks a question and I don't know the answer, I don't mind saying I don't know, and we'll find a good answer. In my tenure here, I started as a test technician, testing machines. And at the time, test technicians also did field service calls. Progressed on, I did some circuit designs, a couple circuit boards here. I've been service manager, technical writer, and probably a few other things. I think that's probably good for that. Our goal here today is going to be to understand the basic operation of common inverter circuits. There's tons of ways of building an inverter out there, and I'm going to cover the two that are probably most used in the industry, being the ferroresonant and pulse width modulation. I think pulse width modulation is probably more prominent, certainly with most manufacturers. SCI still builds our old standby ferroresonant inverters, and we'll talk a little bit about that. We're going to then move on into the static switch and see how static switches work, and hopefully clear up some misconceptions there. We're going to talk about the actual switch, how it works, and various options of making a static switch, and also the monitoring circuits that determine which source of power we use to power the critical load. I'm going to then talk about some specifications specific to inverters and what they mean, and we'll see the differences between the ferroresonant type system and the pulse width modulated type system. And we're going to finish up with a little bit of troubleshooting here. Our training class runs, depending on what it is, 2 to 4 days. And I'm going to try to condense all that into a few minutes. So that'll be a challenge there. We're going to start off with the basic one-line diagram here, just a little refresher, or for anybody that's not familiar with this. We call this a double conversion UPS. We bring incoming power in, AC, typically 480 volts, 3-phase, go into a transformer. And if you were at my last webinar, I spoke only about transformers, and we feel pretty strong about having an input transformer. So we go into a transformer, into a battery charger, and it rectifies the AC input to DC and charges the battery, and then sends that DC onto the inverter then. So the inverter is the second stage of what we call a double conversion system. So first we convert AC to DC and then back to AC again. Okay? The inverter takes that DC and switches it off and on continuously to make AC. And we'll see where our ferroresonant inverters switch the DC off and on at a rate of 60 hertz. And then our pulse width modulated inverters switch at a very high frequency to synthesize and 60 hertz output. Of course, we do 50 hertz if necessary, but by far 60 hertz dominates here. The inverter isolates the output from the input, and it must regulate the output voltage. And when we say regulate, we mean regardless what happens to the DC input voltage or what the load is, we want the output voltage to stay the same. So taking, for example, a single phase inverter, which is normally 120 volts on the output, our DC input, when we operate on batteries, assuming a 60 cell battery, will start at 135 volts and go clear down to 105 volts, in which case we shut down for low DC voltage. But during that period, the output voltage of the inverter has to stay constant. So we have to find a means to do that because the load wants to see a constant voltage or 120 volts. And of course, if from anywhere from no load on the output to whatever the rated output is, we want that voltage to stay the same also. So looking at inverter type circuits, what I'm showing here is a mechanical inverter, which was in use to a limited degree before we had solid state devices and even vacuum tubes. And believe it or not, this little circuit here using relays and the contacts from a relay will generate a crude AC voltage. And that's what I show on the oscilloscope screen here. And the blue waveform is an actual square wave right here. And here is a picture of an inverter used in the 1950s. It's a mechanical inverter. The blurred image on the left I grabbed off a website. And here is this inverter that you plugged into the cigarette lighter of your car, and it allowed you to use your electric shaver while you're driving to work. So distracted driving has been going on for a long, long time here. I can't imagine trying to shave and drive to work, but that's what these things were for, and apparently they sold quite a few of them. So today, of course, we use solid state devices for our inverters. And next thing we're going to look at is our output waveforms. We've got a couple types of inverters we see out there. There's what they call a modified sine wave. And these are common if you go camping, or maybe you have an inverter in your vehicle because you want to run some 120 volt device. You can get these things. They're fairly inexpensive, and I've got a couple of them. And they take 12 volts DC and give you 120 volts AC on the output. They're very crude, but they work reasonably well for certain things. And the other type where we see the modified sine wave type are offline UPSs, generally smaller ones. And we'll have a look at one of them here. Of course, anything Amatec builds is going to be a true sine wave double conversion type UPS. On the left here is the 750 watt inverter. It's actually my inverter, and I did a few tests on this. And we're going to see the test results in a minute here. On the right is a small 250 VA, or a 0.25 kVA offline type UPS. And actually, I've got one of these on my router at home. A friend of mine sells them, and they do their job. Of course, we don't want cable TV to go down just because we have a power outage or anything like that. So I've got one of them myself. Here is the output of that inverter I showed you, the little camping inverter right here. And I put some load on it, resistive load, light bulbs and things like that. And I looked at the output voltage with a true RMS meter, and then again with the standard inexpensive meters you buy at the hardware stores and Harbor Freight and off Amazon and things like that. And we're comparing the voltage these meters read. Now, Fluke used to make, I don't know if they still do, their 70 series meters, which were great little meters, but they were not a true RMS meter. Our industry today pretty much uses Fluke 87s or something maybe a little more advanced than even those. And of course, they are true RMS meters. So we're going to see the effect of this inverter here. So here's at 100 watts, and the pulse width widens. If you notice, I'll go back here. The pulse width here is fairly narrow at no load, and then it widens right here as we put a little bit of load on it. Okay. Now you notice the AC voltage, the true RMS voltage, is staying pretty constant right here. And here's 300 watts, and the pulse width is a little bit wider, not much, a few milliseconds. And notice the non-RMS meter now is reading 106 volts AC. And the true RMS, the Fluke 87, is still right around 115 to 116. Here's at 500 watts, okay, or 550 watts. And our RMS meter, non-RMS meter, is reading closer to the true RMS value because we're approaching a square wave here. Now, again, this is what they call a modified sine wave. And I say, yes, it certainly is modified. It's a long ways from what we would think of a sine wave. But anyhow, that's what we've got right there. Okay. So, advantages of the modified sine wave inverter compared to a modified sine wave inverter. I've got this backwards. The modified sine wave, I've got these backwards, is smaller machine. They are not compatible with with all loads. They don't clear faults. And these are actually the advantages of the sine wave, the full sine wave inverter. They focus on reliability. Full sine wave inverters are physically larger than the modified sine wave, and they cost more. So the modified sine wave types are generally used in commercial buildings for office applications, that type of thing. Here's our ferroresonant inverter waveform, and that's what we're going to look at from here on out, is the pulse width modulated and ferroresonant systems. On the left is the ferro waveform, and you see there's a couple little bumps on the waveform right there, and that's due to a compensating circuit to get us right within our regulation spec right here. But as you can see, that's a pretty decent sine wave right there. And over on the right side is a pulse width modulated. Now we start off with about a 8 to 10 kilohertz switching frequency, and then sort of synthesize a kind of like you do with on computers with sound programs and things like that. Synthesize this 60 hertz waveform, and it looks just about as good as it possibly can right here. Just a little bit of stuff on the very peak there, but that's a pretty decent waveform right there. So next we're going to look at some inverter circuits, see how they work. Here is our outdated, antiquated, exceptionally reliable analog inverter right here, the ferroresonant type system. We still build these for nuclear plants. Things we've been building since the 70s, but they're still great machines. So we start with an inverter bridge, or we'll start with DC over on the left here, and we go through a breaker, and a capacitor bank. And the capacitor bank there stabilizes the incoming DC. And then we're going to see later, it also absorbs kickbacks from the inverter bridge. We go through a fuse, and then I'm showing contacts right now for switches. Later, we're going to see those become SCRs right there. So if we close two contacts, we'll assume our voltage here is 135 volts DC. If we close contact 1 and 3, we're going to have a plus on the left to a minus on the right, and our full DC voltage across the primary of this transformer. And all we care about right now is the primary. And these contacts will be on for exactly half of a 60 hertz waveform. So they'll be on for 8.3 milliseconds. And it's critical that it is exactly half of a cycle. If it's just a slight bit less than half a cycle, that introduces a DC offset on the primary of our transformer, which is going to cause heating and all kinds of troubles. So those two switches are on for half a cycle. Then they turn off, and we turn on 2 and 4. And if you've noticed now, the polarity is reversed across the primary, the transformer. So we've got our full square wave right above the little picture there, above the primary. So we got a square wave. Of course, that is AC because it's switching off and on at 60 hertz. So we've successfully converted DC to AC on the primary of this transformer. And we've got a square wave there. Here's the actual inverter bridge, our analog inverter bridge using SCRs as switches. And there's a typical picture of a inverter bridge. Now, at the top, you see there are heat sinks, and there's the red pigtails are the SCRs. There are 4 of them. And then right below the heat sink, the black cans down there are the DC capacitors. And it's no accident that they're mounted as close as possible to the inverter, because we want very low impedance between the capacitor and the inverter bridge. And just to the left are some silver capacitors connected with bus bars. And those are C2 in the schematic here. Those are what we call the commutating capacitors. So if we gate on SCR1, Q1, and Q4, that shows a current path through the bridge. And we have our, again, our plus to minus voltage, our full DC voltage across the primary of the bridge. Now, of course, there's a voltage drop across the SCRs, half a volt or so, but for all practical purposes, we've got our full DC voltage across the bridge. Those SCRs are on for half a cycle. Then they turn off, and we'll see how that happens in a minute. And now we turn on Q2 and Q3. And we've now reversed our voltage on those across the bridge of the primary there. So we've got our full square wave. And if we take a fluke meter and read across that, it'll read in the neighborhood of 135 volts AC across the bridge. Now we got to figure out the SCRs and how they turn off. So when Q1 and Q4 were turned on. At the end of their cycle, we remove the drive signal, and we then turn Q2 and Q3 on. And for a very brief instant, all four SCRs are turned on, and the current tries to go really high. And so CH3 and CH2, those we call commutating chokes, they hold off the current from rising real fast. And our capacitor C2 sneaks in there. And I don't show the discharge path here because it's kind of complex, but it forces the SCRs off at the end of their cycle. So Q1 and Q4 turn off when Q2 and Q3 turn on. Okay, so we call this a forced commutated bridge. And so it continues operation like this for years and years at a time. And these SCRs have to switch every time at the right time to turn on and turn off for this thing to keep operating. And what continues to amaze me is just how reliable these things are. So anyhow, once the SCR turns off, there's excess energy in the bridge, and we dump that through these what we call clamp diodes. And the diodes just steer that energy back out of the bridge and into the electrolytic capacitor C1. So we think of C1 as the filter for the DC, which is its primary function, but it also has to gobble up the excess energy in the inverter bridge. And so we have to size the capacitor C2 for full load current, but at light loads, we've got more energy than we need. So that's how we get rid of it, is through the clamp diodes. So when we take temperatures of the inverter bridge, like when we test the machines, the SCRs run hottest at full load, which is no surprise to anyone. But the diodes, they run hottest at no load because they're working the hardest, and they have almost nothing to do at full load. And it took us a while initially to realize that. We always assumed everything got hottest at full load. And then we found out we need to check temperatures for diodes at no load. And if you have the manual for one of your inverters of this vintage here, or actually any machines we make, if you have the test data, we record all those readings in the test data. So that's our older generation forced commutated SCR-based inverters, and we still build those on a limited basis. But today we use, for a switch, these things called IGBTs, or insulated gate bipolar transistors. And just by looking at the picture here and the schematic, there's a whole lot less required to accomplish the switching off of DC to make AC. This is a 10 kVA bridge right here. There's only 2 transistors required, and a small circuit board mounted to each one for the drive signal. And the capacitors you see right there are what we call snubber capacitors that protect the transistors from switching transients. So we're back to using a switch here to turn DC off and on. So in this bridge, the DC comes into the center tap of a transformer, and we turn S1 on. And so we drop the full DC voltage across the center tap to the end. And you may notice I show some dots on this transformer, and these dots are the polarity. So when we look at the primary, you see a plus to minus across the primary, and the secondary, the dot is going to, or the secondary is in phase with the dot at the top of the primary. So that's why we show a negative half cycle coming out of the secondary. Now, actually, it would be a square wave, but we're going to clean that up. So that's why I show half a sine wave there. So that switch will be on for approximately half a cycle. Then it turns off and we turn on the other switch. Okay. So now our voltage is plus, still plus to minus across the transformer, but it's the other half. And now we are inducing the positive half cycle in the waveform here. And coming out of the system, we have our full sine wave coming out. And there is the square wave that would be across the primary. Okay, so again, we use IGBTs, otherwise known as insulated gate bipolar transistor. And briefly, the IGBT is the closest thing we have today to the ideal switch for DC. Unlike an SCR, it only requires a little bit of power in milliamps to turn it on. And the great advantage is when you remove the drive signal, it shuts off. The SCRs have to be forced to turn off when they're switching DC. So it greatly reduces the inverter bridge. So that's the two types inverter bridges we use on our ferro-resonant inverters. And here now is the schematic drawing, or a simplified drawing, I should say, of the ferro-resonant transformer. And I need to ask you guys to go out to our website at Amatec Solid State Controls. Go look at the white pages out there. We've got a number of documents out there, and I just got one loaded up there. It's at the bottom of the list that discusses ferro-resonant transformers and everything there that you'd ever want to know about how these things work. And that document, for many people, also doubles as a cure for insomnia, because it does get technical, and there's some things in there that will stretch your attention span. Now, I'm going to try to summarize it right here. We're only going to be concerned about the secondary of this transformer. The primary, as we've already discussed. So we're going to induce a voltage from the inverter bridge into the secondary, and it's up around 600 volts or so. Now that's going to go through an inductor, what I show the choke right there, and the inductor works with the capacitor C805 to form the resonant circuit. Okay, so, and it resonates at 60 hertz. Now every time we switch the voltage off and on with our inverter bridge, of course the polarity changes across C805, and that voltage starts rising very rapidly. Our saturable reactor out here is a transformer that's designed to operate in what we call magnetic saturation. A transformer in magnetic saturation has a voltage that's fixed across it. You can't push it higher. As the input changes, once the transformer hits magnetic saturation, the voltage just won't go any higher. It doesn't matter how hard you want to push, it doesn't go any higher. And so that voltage is in the neighborhood of 600 volts or so, and we tap off of that at 120 volts. So what that does is allows us to have 120 volts coming out, sine wave. Now we have to filter it, but we'll filter it, get us a good sine wave. And the reason we do it like this is that when we operate on batteries, as the primary voltage decreases, the secondary voltage stays the same. So it's kind of a brute force method here. You just run that transformer right into magnetic saturation, and our voltage is fixed then. It doesn't budge. And that goes from no load to whatever full load is, and actually beyond, because these things will operate generally up to about 125% of their rating. Another nice thing inherent in this transformer is it is what we call current limited, and you can drop a crowbar right across the output of the transformer and it doesn't blow fuses or shut down or anything like that. The output voltage just goes to zero, and it'll sit there and run at about 150% of its rating into a dead short. So one application we see for this transformer is in battery chargers, a simple battery charger. We set the output voltage we need, the AC voltage, rectify that to DC, but it's also current limited, so we can have a large battery with a small charger, and we can't overload the charger with this ferroresonant design. So that's another advantage of this type of transformer. Another advantage that's going to become, we're going to see when we get to a static switch, is there's stored energy in the magnetics of the transformer here. So if we lose our primary voltage, we've got about a half cycle of stored energy that'll ride through that loss of AC on the primary. And that allows our static transfer switch to detect a potential inverter failure and get to the bypass, and the load never knows the difference. So it's an easy way of detecting inverter failures. It's pretty simple. Here's again the characteristics of a constant voltage transformer. Regulated output voltage. We put some filters on it, and we put a square wave in, we get a sine wave out. It's current limited. It'll run into a short if you want it to. And there's stored energy in the magnetics there for ride-through capability. Years ago, an offline type UPS used a ferroresonant transformer, and there were a couple manufacturers out there that made these things. They used a ferro as a line regulator, and on normal operation, you brought your whatever your normal line is into the transformer, and you got your output voltage, whatever you wanted it to be. And then if you lost normal AC input, then an inverter bridge started up, okay? And they use the ride-through capability of the ferro transformer to make sure you didn't lose power during the transition there. And these things worked okay. The downside was if you had a very unstable power source, they would be constantly switching back and forth between batteries. So that was a potential problem. The manufacturer liked to call this an online UPS, and the industry didn't quite agree. The guys that made these things were really good at marketing, so they claimed they had a static switch here because of the switch on the primary up there, but that's not what a static switch really does. The downside of this type of design, because there is no actual static switch in here, a capacitor failure on the secondary of the transformer takes the output voltage to zero, and you lose the load then, and there's no way to recover from that. So these things found their home in commercial applications, generally smaller businesses, things like that. They had critical loads, but not the type we see in industry. And I used to cringe when I'd see one of these machines at a power plant or refinery or something like that, because they didn't have the critical static switch they needed to be fault tolerant and so on. But they were out there, and I think they've mostly gone away at this point. One other note, I show a manual bypass switch on the output here. This transformer, the Faro, another characteristic is there is a phase shift between primary and secondary depending on the load. And as you approach full load, it's about a 90-degree phase shift. So when you put a manual bypass switch in, typically it's a make before break, but you can't do that on this type of system because you tie, if the machine's close to full load, you'd be tying two sources together during the operation of the switch. They're 90 degrees out of phase. That's going to have a huge circulating current and possibly trip breakers. So these switches had to be a break before make on this type system. All right, that's the Faro system. The next thing we're going to look at is a pulse width modulated type system. So we're taking DC in here, going to an inverter bridge, and we show transistors there, IGBTs in the box. And we're going to be putting a synthesized AC waveform on the primary. Then we're going to hang a capacitor on the secondary, and it's going to smooth out the waveform, give us a nice pretty waveform. Now in this type system here, we have feedback networks. We send the voltage back to a controller and the current back to a controller. And the controller then times the switching of the transistors to get us our proper voltage, our output current we need. We have to limit the current if it's overloaded or short-circuited, things like that. And our microcontroller does all that for us. Years ago, analog designs had to do that. And there's some pretty good ones out there. But today with the microcontrollers and microprocessors that we have, the controls here work great. And the only thing is the manufacturers don't like to support them very long, so it's a constant battle to get spare parts for our machines. And as many of you know, we try to support these things 20 plus years, and it's a constant battle to get all the parts that are not counterfeit to keep these machines, the older machines, going. All right, so what's modulation? We talk about pulse width modulation. What's all that mean? Well, we take a carrier signal and some kind of modulating signal. Now in radio transmissions, the carrier is the frequency that we tune in on our dial, and the music or voice or whatever we're transmitting is the modulating signal. That goes into a modulator and in the course of a radio, then out to a transmitter. And we have various techniques. So here is amplitude or AM radio modulation. So our audio signal modulates the amplitude of the carrier frequency. And then when our radio receives this signal, it strips out the carrier frequency, and we're left with our audio then. Now, being amplitude modulated, this can be impacted by overhead power lines. And so that's why when you're driving in your car with an AM radio on, you get under power lines, all you hear is 60 hertz hum and buzz and noise and stuff like that, because the radiation of the power lines is an amplitude modulation. Well, to counteract that, we have frequency modulation. So now the amplitude doesn't change, but the frequency is modulated. Okay, so that's good for radio transmission. For building inverters, now we have pulse width modulation. So we're switching transistors off and on at a high frequency, but each time we do that, we change the ratio of the on time to the off time. And that's why we call it the pulse width modulation. So here's our inverter bridge once again. And we're just showing our low pass filter again on the output here. Here is the current path through the bridge. So when we have the two transistors A turned on, we show the current path through the bridge, and there's the polarity across the primary. Okay. And these are switching off and on at a rate of 8 kilohertz. And there will be about 65 of these pulses on the positive half cycle. And you can see here as we go through the cycle, the on time of each pulse gets longer and longer till we get to the peak, and then it starts getting shorter again. Okay, and we're going to see a little better view of this here in a minute. So transistors A, the two A's, are switched on for the positive half cycle, then they shut off and they stay off. And now the other two transistors, the ones marked B, start switching, but the current flow and the direction of current through the transformer is the opposite now. And so our voltage across the bridge changes in polarity. And these two transistors now switch off and on and off and on and off and on 60 sometimes for that half cycle. And again, you can see the ratio of the on to the off time is changing throughout the cycle. Here's kind of a blown up view showing, again, the pulse train throughout a cycle. The average voltage for the first pulse on the left right there, the average voltage is going to be relatively low, and that's what we show at the bottom, for that cycle. Now, again, the frequency of the cycle doesn't change, only the pulse width changes, and then the next pulse we're on for a longer time, so the average voltage is longer for that pulse, and now we're building our voltage across the primary till we get to the peak, and then they start getting narrower again. And then here will be our waveform for the primary of our transformer. Okay, so we've got our plus and minus half cycles made up of lots of individual pulses to create that or synthesize an AC voltage there. All right. Now we send that through our capacitor. And again, it's just a low pass filter. Okay, so it strips out anything above 60 hertz. And we get our nice clean sine wave coming out. So the inductor you see right by the green arrow up there, that also works along with the inductance in the transformer with the capacitor on the secondary to give us our nice clean square or sine wave coming out. That's how inverters work. Whether it's a brute force type in our old analog systems, where we just put a 60 hertz square wave on a primary of a transformer, or we use it with high frequency switching, which is today's preferred technology. We're just finding a way to convert DC to AC. Now, kind of a popular thing some vendors are doing these days, they don't even put a transformer in the inverter. Of course, that saves money, saves space. You have a smaller cabinet and so on. That's okay for certain industries. We don't like that for the industrial application. Our prime clients here, the power plants, the refineries, chemical plants, paper mills, what have you out there. We want to see that transformer in there because it provides isolation, which is critical, and it also provides safety for the electricians and technicians working on these machines. Okay, so now we come out of the inverter, and the next thing is we're going to go through our static transfer switch. The purpose of the static switch is to protect the load. That's the only thing it does. It says protect the load. And you've got two sources of power, an inverter and a bypass source or alternate source. They mean the same thing. And the static switch selects the best source of power under all conditions. Okay? And we look at what do we have to do whatever you have to keep the load up. Never lose the load. Okay? So again, under normal conditions, meaning we've got our normal AC input and running into our battery charger and converting it to DC and charging the battery, the inverter is going to be our best source of power. It's isolated from all the surges and transients going on in the plant. Our battery acts like a huge filter to make sure none of the noise on the input ever gets to the output of the inverter. And of course, it's backed up with the battery, the inverter output is. So if we lose AC input, as the voltage from the charger goes to zero, the batteries are standing there and they just pick up the load. Okay. Let's say we have maybe an overload downstream. An overload or potential inverter failure, either one. The static switch has to detect that. And our biggest concern is an actual inverter failure. We have to detect inverter failure, disconnect the inverter from the load, bring on that bypass source, and accomplish that in 1/4 of a cycle. A 60 hertz cycle is 16 milliseconds. 1/4 of that is 4 milliseconds. So at all times, anything can happen, and we have to detect any kind of abnormality from the inverter, which could also include overloads in the output. And it says, get to the bypass source. Okay? Now, what we're going to see later also, the bypass source may not be available. So in that case, you got two choices. You can say, sorry, I'm going to protect the inverter and shut the inverter off rather than transfer to a dead bus, or transfer to a dead bus and protect the inverter. We take a different approach. We say we never want to transfer to a dead bus. Even if our inverter is overloaded, do whatever you can. Keep that load up and going. Okay? Now, to make sure we have a zero break transfer and we don't interrupt the load, we have to synchronize the inverter to the bypass source. The actual transfer between inverter and bypass is break before make, and they parallel together during the transition. So it would be critical that we keep the inverter synchronized to the bypass source to make sure we have a clean transfer. Now, if we're in an area where the voltage, the bypass is unstable, we see this sometimes on platforms or in other countries, remote areas, things like that, where they don't have a stable grid. If that bypass frequency goes off, well, we don't want to track it too far, so we put limits on how far we'll track that. Here's some of the monitoring things we look at to determine which source, the inverter or the bypass, is powering the load. So we've got bypass source availability. We certainly want to know if that's available because we don't want to transfer to a dead bus. We look at inverter output voltage. We look at inverter output current. The heat sinks where the transistors are located. If we have an air conditioner, hopefully we have it in an air-conditioned room. Maybe it's not. Maybe it's out on a turbine deck where it gets to 130 degrees. I've seen that before. I've worked on an inverter that ran on a turbine deck that was in the open air. And in the summer, it was running at 130 degrees Fahrenheit. The machine was only rated for 105 or 40 degrees C. And this machine sat out there and ran and ran and ran. And I told the guys, hey, you might want to get this air conditioned. And the response is, well, in the winter, it's colder. Okay. So we do monitor heat sink temperatures. Okay. If it gets excessively high, we're going to shut the inverter off to protect it from failure. Now, of course, you don't shut it off if the bypass is not there. You tell the inverter, I'm sorry, you're going to have to keep on running and hope that you don't fail. Okay, so we monitor heat sink temperature. We monitor the actual current through the bridge. Of course, we monitor DC voltage. And the brains of the whole operation, the microprocessors, there are monitoring circuits on them to say, hey, is this microprocessor doing the right thing? Is it okay? So there's all kinds of things that go into the controls here. And again, all the decision process is protect the load at all costs. Avoid ever dropping the load, including potential inverter failure. We may risk inverter failure if we have to avoid dropping the load. You can rebuild an inverter a lot less expensive than restarting a plant. Okay? So once we detect something is wrong, we have to do a quick transfer. Now, the means of which you do that, there's several options out there. One option is you can use contactors. Another option is motor-operated breakers. The thing with that is a contactor, if you want to pull in a contactor as your switch, first of all, you've got contact bounce, which generates arcs and things like that. And contactors are slow to operate. And we're thinking here cycles, or a minimum of a cycle to pull in or drop out. That's way too slow for what our needs are here. Another option is motor-operated breakers. The same thing. They take time to operate and certainly not going to do it in a quarter of a cycle. So SCRs become the preferred means of switching. And then there's some people use a combination of SCRs and contacts as their switch. So here's a static switch. They're using, and there's a variety of ways they accomplish this, where they put the contacts and the SCRs and so on. But when they go to the bypass, they put an undersized set of SCRs in for the fast transfer, but they're not intended for continuous operation. The one nice thing about SCRs is their overload capability. Let's say you have a 235 amp SCR, which is pretty common. For parts of a cycle or so, for fuse clearing and so on, these SCRs can withstand about 2,000 amps. So they have a really high overload capability. So you can put a very small, in this application here, set of SCRs in, take advantage of the fault clearing or the short-term current capability of the SCR, and use that to initiate the transfer while you bring in a contactor. I don't really like this idea because I don't want to rely on a mechanical device and the arcing contacts and potential of that. But that's an inexpensive way of doing it. And so we have a contact for the inverter side and one for the bypass side then to make the switch. Here is the approach that Amatec uses for all of our static switches. We put in big SCRs in there. And we know that these things may see 150% overload, or the rating is 125% continuous. So we oversize the SCRs. We oversize the heat sinks so they can run continuous. And this is a very reliable static switch here. The only question is now what you use as a gating circuit. Somehow, if you recall, I said, always get to the bypass source if it's available. Well, if our control circuits fail and our power supplies fail, we can't use that as an excuse of why we can't get to the bypass. So we're going to find a way. We have to be able to make sure we can always gate on the bypass source. If we have all kinds of failures, get to the bypass, and that includes power supplies and things like that. So we'll see how that happens here. Before we get to that, I'm going to show you just the current path through the static switch. On the left here, we've got the inverter, and we come in, and I've got it labeled green right here. And the voltage splits and goes two directions. On the positive half cycle in yellow right there, the current path is through Q7 and on out to the load. And then on the negative half cycle, the polarities reverse, so the SCR conducts during the negative half cycle. And on the output, they combine back together for our full sine wave. Now the colors I use here are not a coincidence. If you recall, you put blue and yellow together and they make green. So that's why I show it in green here on the input and output, and then dividing and going different ways for the two halves of the cycle. Of course, if we swap to the bypass, we have the current flow on the image on the right side. And Q9 now, because the voltage across the static switch from top to bottom is going to be plus to minus during the positive half cycle, Q9 conducts, and then the polarity across the bridge for the negative half cycle reverses. So it's negative on top, positive on the bottom. So Q10 conducts during the negative half cycle, and we have our full sine wave on the output. And you notice I show a little current transformer on the output right here. That's where we detect our output current. So how do we gate on the SCRs? We're going to use SCRs as the switch, but somehow we have to tell them when to turn on. So there's a couple means of doing this. And most of the vendors out there use some kind of a high frequency pulse train right here. So they've got a gate drive control circuit, and similar to what we do for a pulse width modulated inverter, we send out a string of pulses that tells the SCRs to turn on at the right time. Okay, and this works pretty good. The downside, though, is if your power supply fails or your drive circuit fails that's sending out these gate pulses, you lose the load. So you dump the load then. So you can build redundant power supplies and so forth, but there's still that possibility that you can lose the load. So we take a different approach to that. Again, here is the static switch, but this time I've stripped all the colors out of here. And looking at the inverter section, you'll notice there's a contact right there. This is a read relay. When we load on inverter, the contact for between Q7 and Q8 is turned on, and the SCRs now self-gate themselves. So on the positive half cycle, again, we've got plus going into the bottom of Q7, and we have a current path through those two resistors, through that contact, and that puts a plus on the gate of Q7 and turns it on. So the inverter source is also the gate drive for Q7. And now when we reverse polarities for the negative half cycle, all the polarities reverse, and the the inverter now supplies a gate drive signal to Q8, so it conducts during the negative half cycle. When we swap to bypass, then on the right side, you notice the contact is closed up at the top there, and that contact is what powers the gate drive to the two bypass SCRs. So the great thing about this is we want to swap to the bypass. Maybe our power supply or our gate drive circuit failed. No big deal. The bypass contact is the normally closed contact. And so we drop out the relay and it defaults to bypass then. So we need no other controls. As long as we got bypass voltage, the contact is closed. When you transfer to inverter, you energize the relay. That's how the inverter gets its gate drive then. Here's the current path. Again, for the positive half cycle, I'm just showing this going through here. So the contact here is not just an ice cube relay. It is a read relay or a read switch. If you're not familiar with them, the read switches have a number of characteristics that make them ideal for this application here. So first of all, a read switch, unlike a typical relay, uses two contacts that are biased either closed or open, whichever you want, with a magnet, and then the coil of wire is connected such that it bucks out the magnetic field of the magnet, and that's what allows the contacts to change state. So reed relays until the last 20 or 30 years were very common in voltage monitoring and detection circuits, sample and hold type circuits, things like that. I believe the phone company used them in their switchboards because, again, reliability. I've read that they're good for literally millions of operations, primarily because they really don't have any moving parts. The contact internally is hermetically sealed, and so you don't get corrosion or anything like that. So life expectancy is really good. And the primary reason we use this is because they're fast. An ice cube relay, like the old Potter Brumfield that everybody's seen before, those relays take around 14 milliseconds to change state, close to one complete cycle at 60 hertz. It takes for one of those relays to change state. They're far too slow for use in a static switch. The reed switch, on the other hand, will go in about 100 microseconds, or what's that, 1/15th of a cycle, something like that. Actually 150, I think. They're super fast. So they're the ideal thing to use to make a reliable static switch. Okay. Now what we show here is an actual transfer from bypass to inverter. And I'm going to give you a minute to look at this and see if you can determine when the actual transfer occurred. On the left is the bypass. On the right is the inverter. Okay. Where did the transfer occur? Is it up at the top there? At that peak? Maybe the bottom peak? Where did it occur? The answer is, I don't know. But somewhere in the negative half cycle, because if you look closely at the peaks of the negative half cycle right there, they're lower than what is the inverter. And I recognize that's a ferroresonant inverter. See, it's got a couple minor little bumps on it. So the peak on the negative half cycle, the first negative half cycle, is lower than the peak of the positive half cycle up there. So somewhere in the negative half cycle, the transfer was initiated, whether manually by a push button or because of some detection. But because they parallel together during the transfer, you don't notice any interruption. Now, right at the zero crossing right there is where they separated. But where the actual transfer occurs, we don't know. Now, when we do testing at the factory here, or when our field engineers come out to your plant and work on the machine, we set up our oscilloscope and we do transfers as part of our PM process. And what we do is we use a current clamp as the trigger on the oscilloscope to monitor if we're transferring to bypass when bypass current is detected. And that's how we trigger the scope to capture the waveforms then. Okay. But all we know is we show the trigger on the scope to know where we told it to go, and then we show the waveform, the actual transfer then. Okay. So if you get one of our PM reports, you'll see the waveforms that we capture as part of every PM and startup. Now here's I threw this in here. You may recall earlier on in the the slide or in the presentation, I showed you the little offline UPS. This is the output of that offline UPS when the AC input failed. And you can see in the picture in the left there's a little bit of a break right there where the sine wave went to 0. And that's offline system has to detect the loss of output voltage. And then it has to start the inverter. And so the little flat line there is the detection time. And then that inverter starts up. And here's your modified sine wave. And this is that I captured this off that little UPS there. Now, when you're just running a computer like a desktop computer, which has switching power supplies in it, they'll run fine off this thing here. Now, you'll hear 60 hertz hum and buzz a lot louder. And you may even, if you've got speakers in your computer, you'll often hear that through the sound card. But the computer will make it through there. And if you're using this on your router at home and whatever gadgets you've got to make sure you never lose internet and so on, these things work okay there. I'd certainly never want to put them out in industry for a critical load of a process or anything, but they work okay for home use. Motors aren't going to like this and some other things like that, but for the average computer, they work fine like that. All right, that gets us to specifications for inverters. And as you may know, we build both a ferro inverter and a pulse width modulated inverter. And so that's our pulse width modulated system is called DPP for digital process power. Okay. And so we show voltage regulation at the top here. The ferro is plus or minus 2%, and that's far more than adequate than any load will ever need, but that's the spec. Okay, now keep in mind this is a passive type regulating system, so the secondary voltage does not have a controller to monitor it and make corrections. But because the ferroresonance design, it works great. So we're able to keep 2% regulation there. The DPP system is a plus and minus 1%, far more than adequate. But because we've got great microprocessors that are super fast, we can correct output voltage really fast and maintain that 0.5% or 1% regulation. Now, the next thing is called slew rate. Okay. Most people never worry about that. It doesn't come up very often, but slew rate is how fast the inverter tracks a bypass source. Okay, so let's say we've got maybe a generator that's the bypass source, and it's not real stable, and it's got a lot of load on it, and maybe its frequency is constantly hunting. And if it changes too quickly, too fast, that can jerk the inverter around who's trying to synchronize to it. So we limit how fast the inverter will track a generator. And this is primarily not for the benefit of the inverter, but the benefit of whatever load we have out there. If something is sensitive to a change in frequency, we don't want to cause problems with it. So the inverter will track a generator as long as it doesn't change frequency more than 1 hertz or 1 cycle per second. Okay. Once we do synchronize to the bypass, we also look at the actual frequency. So we look at two things for synchronizing: how fast we want to track that, and then how far out we want to track it, how far the frequency goes. So again, here in the US, we've got a stable grid here. So we're not too concerned about being right on 60 hertz. But in other areas where they don't either have a grid or it's not as stable, we have to limit how far we track the bypass. So anytime we go out of limits, then the inverter does what we call it breaks synchronism and reverts to its own internal clock, which is set right on 60 hertz. So it syncs to its own reference then when the bypass is not acceptable. All right. Next spec we have here is crest factor. And crest factor is the ratio of the peak current to the RMS current. Now, if it's a sinusoidal, or let's say a resistive load, our waveform would be a sine wave or sinusoidal current waveform. That has a crest factor of 1.7. Okay. Switching power supplies will have a crest factor because they only draw slugs of current at or around the peak of the waveform, may have a crest factor often well over 2 to 2.5. And we set our overcurrent detection circuits to tolerate up to a crest factor of 3 to 1. So that's a really high peak current relative to the RMS current. Okay. Years and years ago, this detection circuits were just a peak detect based on a true sine wave waveform, when all we had were linear loads and resistive loads, things like that. And in the 80s, when the power supply started showing up, it caused problems. So we had to redo the detection circuits. So it's important that the inverter now is able to respond and not detect an overload, even with a high crest factor. Okay, so that's all just in the controls. Transient response is how the inverter responds to a sudden application of load. And the typical spec is no load to full load. What kind of dip will the output of the inverter see when we pick up full load on it? The ferroresonance system, you look at it and you say, wow, that thing is terrible. Well, compared to a microprocessor-based system, yeah, it's not as good. However, there's nothing out there that won't withstand that first half cycle, a dip, and it says 23%. So it looks like, wow, that's not so good, but it's really not as bad as it may first appear. Next thing we see is overload capacity. And this is something, especially a lot of the commercial UPSs won't tolerate. A lot of them won't even go to full load. Our spec here for industry, though, is 120% continuous, 125% for 10 minutes, and 150% for 1 minute. So you've got quite a bit of overload capability in there, and you have to design that in. That means more transistors or bigger transistors for the inverter bridge to supply that. Your cabling, your transformers, everything have to be oversized, but that's what they need in industry. Harmonic distortion on the output voltage of the inverter. Ferroresonant, because again it's a passive type system, has a 5% distortion waveform. The PWM is less than 3%. Now this is total harmonic distortion. And typically they'll do 1%, and the ferros are usually in the 3 to 4%. But that's the specs on them. Keep in mind that most of the loads out there will run on a square wave, the switching power supplies and so on. So it's a nice spec to have, but for most applications, the output distortion does not affect a lot of loads. Of course, there are some very critical things that are sensitive to that. Here's the last one, something we really excel at, ambient temperatures, 0 to 40 degrees C. And there's an asterisk goes with that, says non-condensing or anything like that. But these machines are designed, you install it in there, and if it's a hot room, 40 C is 105 Fahrenheit, they're designed to run continuous at 105. Do the electrolytic caps like it? No, but we put them in there so that they can run for the specified 10-year life of electrolytic capacitors. That's the main thing of temperature. The electrolytic capacitors in the machines are affected by temperature. What we see a lot of times is people say, well, we got a dusty environment. My reference for a dusty environment is the coal burning power plant that never sweeps up or anything, and coal dust and fly ash is an inch thick on the floor. That's a dirty environment. We try to discourage dust filters, primarily because they tend to get forgotten. And so we don't put them on our machines. Most any room you see out there, it's not really all that dirty. And if we're able to do our annual maintenance on these, or whenever you have planned outages, we go in there, do all the inspections, and that's a good time to clean the machine out, clean the dust out of transformers and fans and things like that. But the machine is put out there to sit there and run and not cause trouble. So we discourage dust filters there. If the room gets a little bit warm, so be it. The thing should keep running. It's there to protect your load. All right, here's actual transfer. I got out of our archives here on the left of the ferroresonant system. And you can see in the where they picked up load right in the middle of the waveform there, that on the negative half cycle. And it just happened to be when they added the load was on the negative half cycle. And you can see it dips a little bit there. Okay, but it recovers right away and gets back into its spec right away, and everything's fine. The PWM machine, because it's got microprocessors, processors flying around at megahertz and can respond real quick. On the bottom waveform is the current, inverter current when we picked up load, and the top waveform is the inverter output voltage. And you can see there's not hardly any, even the most minute deviation on that. So when we pick up load, it responds very quickly. Okay. Here is the crest factor waveform that I mentioned earlier. And what all this is showing is just the RMS load current would be the sine wave level there. And then again, for switch mode power supplies, they only draw current spikes near the peaks, okay? Because really the This power supply, the input circuit, is just a rectifier that takes the 120 volts AC and rectifies it right to DC. And it only draws current during that peak right there because it's recharging the filter capacitor in the rectifier. So most of the time it doesn't draw any current. But your monitoring circuits still have to be able to provide that peak current for a short period of time, so we don't have nuisance alarms and transfers, things like that. SCI Amatech has another great document, again out on our webpage, on sizing a UPS. And there's a second document there on fuses and panel boards and breakers, and understanding why you don't just put any panel board up there to feed your critical loads. So there's a couple really good documents out there that explain all that. And I encourage you guys to, when you get a minute, go out there and read up on that stuff. There's some good information there. So we do a 4-day class and we talk a lot about troubleshooting. Now I'm going to try to condense that into a few minutes here to look at just some very brief troubleshooting here. So here's our analog inverter bridge. And as I've said, these things just sit there and run and run and run and run. But something could happen. It could fail. If we're not able to do our maintenance when we need to, our 10-year maintenance, capacitors fail, and then inverters start failing. So if we blow a fuse, F2 at the top there, first thing we're going to do is check the SCRs and diodes. This inverter bridge has two halves, an upper half and a lower half. And if you look at the primary of the transformer, it looks like a piece of wire when we're just trying to check SCRs and diodes with a meter. So it has 0 ohm resistance. So the diodes and SCRs on the bottom half, both the left and right, all appear to be in the same circuit together because the transformer primary has 0 ohms resistance when it's not running. So we can check the two lower diodes and the two lower SCRs, all four of them at one time with our meter on the diode scale. And we look at an SCR or diode failure as being shorted, 0 ohms. If it's not shorted, it's good. So you can quickly check all four of those with a meter, even a cheap meter like this one right here. We don't like to see them out in the plants, but still you can use that to check these guys. And if none of them are shorted, you assume they're good. And then we go up to the top half and put our meter across one diode like that, and it's checking actually both SCRs in the top half and both diodes, because they all appear to be in parallel as far as the meter knows. So we check them. If we don't have a shorted device, we assume they're good. On the other hand, if we do see a short, then we start lifting pigtails or lifting connections, whatever we have to do to isolate them. If we see one that's failed, I'm going to try to discourage you from changing them all out. Because again, these things are very reliable. If I come out to your plant and I'm working on an inverter, if I find a diode or an SCR that's failed, I'm going to change out the one that's bad. And I have a pretty high belief that this thing is going to start up and run again and going to be reliable. On the other hand, if you say, nope, we're changing them all out, I'll do it, but I'll protest first. Okay? SCRs and diodes just don't fail very often. and transistors, which we're going to see next. So it's even easier with the digital ferroresonant type system, which we have here. This is what we call our SE system, SE and SV type UPSs. They use the transistors. And again, the primary of the transformer, when this thing is shut down, looks like 0 ohms. So the collectors of the two transistors, that's the right side of the transistor, all appear to be in parallel. And so if we blow an inverter fuse in the ferroresonant system, we're going to come and check these transistors. And I look from the center tap with the plus lead to the negative lead right there. Now there's a fuse not shown here. This is on the load side of the fuse on the positive lead right there. But we look right across here, and effectively we're checking both transistors at the same time. Okay? In this case, if we see a shorted transistor, we do replace all the transistors here. And the reason is, at the time a transistor fails, there can be high voltage transients produced in here that could potentially damage a transistor but not show it as a shorted failure. I had to learn that the hard way. First few times I worked on these machines out in the field, I had one transistor fail, and I thought, well, we only replace one when the SCR type bridges. I'm going to replace this one. And I had other people tell me, and I said, no, I think I'm just going to replace the one. I think it'll work. A day later, I was back at the plant replacing the other one. So that was a lesson learned. For this type transistorized bridge, if one fails, we go ahead and change out both of them. Okay. Fortunately, they almost never fail, so they're really rugged and reliable. Here's our pulse width modulated inverter bridge. And similar to the other ones we've looked at, now I show a single phase bridge right here. A three-phase bridge has one more set of transistors in it, but effectively the upper half and the lower half of all the transistors are in parallel when the machine is shut down as far as the meter is concerned, because it reads back through the transformers. So we look from the middle of the bridge to the bottom, which is negative, and then from the middle of the bridge to the top, which is positive, and look for a short. If we don't see shorts, then we continue on troubleshooting and go from there. So here's the points that we monitor a static switch for transfers. We look at output current coming out of the static switch. We look at inverter failure, and if there's a load fuse coming out of the inverter, some systems have an inverter output fuse, some do not. If there's a fuse there, we look on the load side of the fuse to detect blown fuse and inverter failure at that point. We also look at inverter heatsink temperatures and over temperature at the actual inverter bridge. Heatsink temperature is just monitored. Many of you guys have seen this, the little round, they call them snap discs or something like that. They're about the size of a nickel with two little leads sticking up and bolt right on the heatsink there. It's a bimetal strip that closes when it gets too hot. I mentioned keypad failures. I hate to admit it, but we've had keypad failures, and I'll apologize to anybody that had a keypad failure. The conditions we've seen, because here's a picture of the keypad right here, took us a while. We just couldn't understand. We'd see a static switch start transferring back and forth and doing this, and a battery charger maybe going from float to equalize. And we only saw this initially right on the Gulf Coast. And we're going, all right, what are these guys in the Gulf doing that nobody else is doing? And just look and say, what is up with this? Finally, we concluded there was moisture getting in the keypad. Okay, because after a little bit, we realized we could disable the keypad. And fortunately, the cable off the keypad here slips right through the front, front of the door here, and it's a cable, a real thin cable that has a connector on it called what we call zero insertion force, and it just slips right into its mating connector right there. So it was easy. When we first saw this happen, we pulled the connector out of the control board and or the display board right here inside the cabinet. And if we had clearance to do that, we'd do it with the machine online. It will not initiate transfers, things like that. So we've been able to disconnect it until we sent out a new keypad. And it's been a struggle to find a vendor that would make a hermetically sealed keypad that will work right there. And then the other thing is they'd like to make 100,000 keypads, and they don't want to sell just 500 or 1,000 or a few thousand at a time. So it's been difficult finding a reliable vendor that would make them to our spec and get them out there. So if you have had a keypad issue, the issue seems to have been somehow humidity gets inside the keypad, and because they're normally open contacts, all these are, get some humidity in there, and they're high resistance circuits, digital circuits, humidity has caused trouble there. So if you've experienced that, we're trying our best to take care of it, but it's been difficult. So accept my apology for that, please. That's it. Any questions at this point?
Okay, thanks for that, Don. So we had one question that I've answered in the chat bar already. It was basically regarding, they said they know a lot of manufacturers have stopped making ferro inverters. Price is much higher than PWM. Does that mean ferro inverter is obsolete? And that is not correct. We do still make the DSE, which is our digital microferro system. And I'm not a salesman. I don't know the price difference, but I know they are very, PWM and our microferro system is very similar in price. Am I correct on that, Don?
Yeah, that's my understanding. I don't get involved with that either, but I don't think there's a wide difference, a huge difference between them. Now, I will say our ferro inverters, we build single phase and three-phase inverters. The single phase only goes up to 50 kVA, and we can build much larger than that, 75, 100 kVA, 125, potentially even 150 kVA. If you want one single phase like that, they do get pretty expensive. So when we get beyond 50 kVA, yeah, a ferro inverter would be, I don't know what it is, but I'm sure a lot more expensive than pulse width modulated type.
Okay. Cool. And we have another one. What are the critical parts expected to fail due to extreme ambient or aging or input power troubles? Well, the extreme ambient and aging is always electrolytic capacitors. So that is the DC capacitors, the big DC capacitors within the DC bus filter circuit, and also all of the DC capacitors that are on our control board. So that's why we recommend and we design the systems so they need to be replaced every 10 years. Every DC electrolytic capacitor manufacturer gives their lifespan in hours versus temperature, and we have spec'd ours out so that they do last 10 years, as long as you don't go above 105 degrees Fahrenheit or 40 degrees Celsius. On the input power troubles, I don't, because it's protected by a transformer, I can't think of anything that input power troubles would have any aging factors on, Don?
No, Craig, you know, I can't see the questions.
That's cool.
Here, but how is the question worded again?
It says, is there any critical parts that could be affected by input power troubles?
No, I can't think of anything. One thing comes to mind, though. Some people use these MOVs, not motor-operated valves, but metal oxide varistors on the input to a UPS. We don't like that because of their failure modes, and we don't ever put them on a system on the input unless you specify it out and want them. But I have seen lots of those fail on systems where they were spec'd out. They just have natural degradation over time. And the thing is, when they fail shorted, and it's a pretty violent reaction. And ideally, they should be fused, but fusing them is difficult because they are there to block surges and transients. But I think our input transformer we have isolates a lot, and we have a surge withstand test that all of our machines go through, and it dumps about 4 kV of high frequency noise into the input of the machine. We run it like that while the machine's running for 1 minute. So our machines are fairly well protected against input excursions and so on.
Cool. Somebody else has asked, is the training recorded such that we can watch it later? There's 2 things. If you signed up for the webinar, you will get a link for a repeat of this. The problem with that link is you have to watch it from the start all the way to the finish. You cannot fast forward it or rewind it. But what our marketing department do is they download the video from the website, and we then put it on our YouTube site. So everybody who attended this class will get the link to our YouTube site. Brooks just posted it in the chat bar there, and you can go and watch that at your leisure. Fast forward, rewind, pause, do whatever you want. So thank you for that, Brooke. So what we'll start to do, obviously this ran a little bit longer than expected. So you got 2 hours for the price of 1, which is always a good thing. And I hope it was interesting information for you. So as we say our goodbyes, if you do have any other questions, we will type it in. We would like to say once again, really, we appreciate your time. We do know that it is precious, and we appreciate you spending that time with us every Wednesday, usually the 3rd Wednesday in every month. You will be sent a link for the new webinar that is coming up next month, and the details of what that will be about as well. And also, if you have asked a question and it's a private question, I'm going to stay on and answer those questions in the chat bar. So do stay on, and I will answer some of the private questions that have been asked as well. So I would just like to say thank you to Don. Absolutely fantastic presentation today. Really, really enjoyed it. Very, very technical. And I hope everybody else out there enjoyed it too. Don't forget, Don is our training manager, and he is in the process of trying to find out how we can get our in-person training classes back up and running during COVID. So we are in the process of making arrangements. So we may be able to do a class in October. We're not sure yet, but we are doing everything we can. So watch out for your emails for that as well. And don't forget, you have all of the white papers that Don mentioned on our website. I put the link in the chat bar if you need any more information. And you can always contact us using the website as well. There's a contact us page. So once again, thank you, Don. Thank you, everybody, for joining us. And take care until next time. It's been a pleasure as usual.